Let's dig a little bit deeper into the second law of thermodynamics, which you'll remember says that the total entropy change of the universe must be positive for a process to be spontaneous. Now, it's kind of difficult to look at the whole universe for every process, so we're going to break it down into the delta S of the universe is just going to be the change in entropy of the system plus the change in entropy of the surroundings. So, if your entropy of your system decreases, then your entropy of the surroundings must increase by a larger amount in order for the process to be spontaneous. So if delta S of your system is negative, the delta S of your surroundings needs to be positive and large for a spontaneous process. So let's think about things like water vapor condensing. It's spontaneous even though the water vapor is more random than the liquid water. And so since it's spontaneous, but our entropy change of the process is unfavorable, there has to be a large increase in the entropy of the surroundings. And that increase in the entropy of the surroundings, in the case of water vapor condensing, is the heat that's released from that process happening. So the entropy increase for the surroundings comes from the heat released by the system. In order for a process to be spontaneous and gain order, have a negative value for entropy, it needs to be exothermic. It has to give off enough heat to overcome that increase in order or decrease in entropy in the system. So let's look at a graph here to kind of bring this together. So if our entropy system is unfavorable, so we're gaining order, the entropy change in the surroundings needs to be favorable and large in order to overcome and be spontaneous, have a positive delta S for our universe. What that means is that the delta S of the surroundings is temperature dependent. When you add heat to surroundings that are cool, it's going to have more of an effect on entropy than if the surroundings were already hot. You can see this in what temperature phase changes happen at. So water will freeze spontaneously below 0 degrees Celsius because the heat released on freezing makes the entropy of the surroundings large enough to make the overall delta S positive. Above 0 degrees Celsius, that increase in entropy of the surroundings isn't enough to make the delta S, the overall delta S positive. So at a low temperature, this value is enough to overcome this one, but once the temperature gets high enough, our delta S of our surroundings is no longer large enough to overcome the delta S of the system. That stays the same number. So our delta S of the universe is negative, and we are not spontaneous at high temperatures. So how do we quantify entropy changes in the surroundings? You may recall from Chem 103 that the entropy change in the surroundings is proportional to the amount of heat lost or gained. So heat is Q, the heat of the surroundings is the opposite of the heat of the system, and the entropy change in the surroundings is also inversely proportional to its temperature. And if we're at constant temperature and pressure, our overall relationship is that the delta S of the surroundings is the opposite of the delta H of the system divided by T. So let's work through a quick problem here using that equation. Calculate the entropy change of the surroundings at 25 degrees Celsius for the reaction below. We're given a delta H value and a temperature. We want to find the delta S of our surroundings. The math problems in this chapter, as long as you understand the concepts of what we're talking about, the math is pretty much just plug in numbers. So here we're given a delta H of our system. So the delta S of our surroundings is going to be the negative of the delta H of the system. So negative 2044 divided by our temperature in Kelvin, because we want it in joules per Kelvin. So divided by 298. So our delta S of our surroundings is equal to 6.86. This is in kilojoules per Kelvin. It asks for joules. So 6.860 joules per Kelvin. So, and that makes sense because it's a combustion reaction, so we should greatly increase the entropy of our surroundings. Here's one where you should pause and make sure you can answer this yourself. The reaction below has a delta H of reaction of positive 66.4 kilojoules at 25 degrees Celsius. Determine the delta S of our surroundings, the sign of the delta S of our system, and whether or not we are spontaneous. So delta S of our surroundings is the opposite of the delta H of our reaction divided by our temperature. So that's going to be 0.4 divided by 25 plus 273 is 298 Kelvin. Gets us negative 0.228 kilojoules per Kelvin, or negative 228 joules per Kelvin. The sign of our delta S of our system, this goes back to the previous lecture, so we have 3 moles of gas on our reactant side, 2 moles on our product side, and so our delta S there is going to be negative for letter B. And whether or not the process is spontaneous, both system and surroundings are negative, so, and they need to be positive to be spontaneous. So we are not spontaneous. So negative delta S, so non-spontaneous.